What I'm going to show you in this video is how to calculate the energy that an electron needs to jump to a higher energy level in the Bohr model. But first, I got to explain electromagnetic radiation. And a more familiar term for electromagnetic radiation is light. So, when we talk about light, there are two ways to talk about light. We can describe light as a particle, or we can describe light as a wave. Now, the wave is historically the older model of what light is. And our models for light, waves, start off with something like this. And there happens to be a couple variables when we talk about light. The first one is this. From peak to peak on a wave, we're going to call that lambda. Now lambda is equal to wavelength. I'm running out of room. Rats. Oh well, but you get the idea. That word right there is supposed to be wavelength. Another property of a wave, and this is all waves have a speed or velocity associated with them, but when we're talking about light waves, their speed is constant, and it is always going to be 3.00 times 10 to the 8th meter per second. Super fast. Speed of light. The last variable is something called frequency, and it's written as sort of a squiggly U, V thing like that, small case. And frequency, okay, and so what frequency is sort of an odd unit. It's as if I were watching this wave go past me, and I as an observer I just looked at one part of that wave. So let's say I'm just looking at the top of the wave. As that wave propagates across, going g g g g g g g g, going like this way across, and I notice this peak, this portion, that's going to pass me at time intervals, and that's what frequency is. It's sort of equal to like waves per second or time, and that's kind of a clumsy unit. So a lot of times it's going to be written as 1 over, the units on frequency are 1 over seconds, or sometimes it's going to be second raised to the negative first, or more commonly it's going to be written as a hertz, Hz. And you're familiar with hertz because there's, that's how you dial your radio to some megahertz frequency. Okay, so that's going to describe a wave of light. Now, in terms of a particle, I have another equation, which is going to be I guess I never put that into a form of equation, so I'm going to do that right now. So the wave, I have this equation. C is equal to lambda mu. And that's going to be important. So, keep that sitting there. Now, as far as back to the particle, in this case, energy, E, is going to equal h mu. This energy, right here, will be in joules. H is a new quantity. It's called Planck's constant. It's equal to 6.6 times 10 to the negative 34th joule seconds. And if you sit there and fiddle around with it, you're going to see why frequency is a reciprocal second, because that will cancel with the second from Planck's constant when you multiply them together, because this frequency is the same frequency that is in the equation that defines light as a wave. So these are the same. So it's kind of a unifying deal. All of a sudden, light was described as both a particle, which this equation does, and a wave, which this one did. All right? So now let me show you how to do these calculations. So let's say I have the Bohr model of the atom. And it's, the nucleus is there, and I have this one energy level here, and then I have a second energy level here, and I don't know what they are. Maybe this is n equal to 1, the 1s, and the blue might be 2s, but it really doesn't matter. But what I'm going to calculate is how much energy it takes for this electron to be bumped up to a higher energy level, then cascade back down to where it began, emitting a photon of light. So that's, how come I can't draw right now? Am I past 10 minutes? No. Okay. Photon. Alright. Looks kind of weird to make that. Okay. So here's what I do. I would observe a color of light. Let's say that photon of light had a color of blue to it. So it was some blue light coming off of this. And let's say that the blue light on a chart I read had a wavelength equal to like 4.5, something's happening here, okay, 4.5 times 10 to the minus 7th meters. All right? So what I'm first going to do is take that. That's where the problem was coming. Get rid of that. All right. So back to this. Okay. Okay. So I know what the blue light is. It's 4.5 times 10 to the minus 7th. I better hurry. So what I'm going to use first off is C is equal to lambda mu. I'm going to solve for the frequency, so I'm going to set this up to be 3.00 times 10 to the 8th meter per second. That's going to equal the blue light, which I noticed when that electron fell back down, meters, times the frequency. If I solve for the frequency, it's going to be 3 to the 8th divided by 4.5 to the minus 7th. I'm going to get, crazy number, 6.67 times 10 to the 14th hertz. Okay? Electromagnetic radiation is has very short wavelengths and is going at a very high frequency. So, okay, so that's part of this. Now I'm going to take that number, I'm going to take the 6 times, and I'm going to take it, continue it to the next page, and now what I'm going to do is I'm going to use E equaling h mu. So the energy is what I want to solve for. H, Planck's constant, 6.6 times 10 to the negative 34th joule seconds times the frequency that I just figured out in the problem before, which was 6.67 times 10 to the positive 14th. And the units there are 1 over seconds, or hertz. So the seconds are going to cancel out, and when I multiply those together, that's going to give me what the energy of the electron, negative 34th, that's going to give me the energy being equal to 4.4 times 10 to the minus